Geometry Unit Section 4. In this section, we'll take a brief look at some additional topics related to triangles. Many applications for triangles come from surveying, where we may need to determine measurements from inaccessible distances. In the automotive industry, when we're looking for center of gravity height, triangles show up. In construction and or metal fabrication, and building trades. So first thing we're going to take a look at is labeling triangles. We use capital letters for the vertices, and the side opposite each of those capital letter vertices is the side length. So here, lowercase a is indicating the length of this side along the bottom of the triangle. Here we have lowercase b is opposite the vertex with the capital letter B. This indicates the length of that side of the triangle. And likewise, here we have lowercase c indicating the length of the side opposite the triangle with vertex labeled C. Here we have a right triangle, and we indicate that by the small box to show that we have a 90-degree angle. The sides opposite the right angle is the longest side. It's called the hypotenuse. And the two sides making up the right angle are called the legs. An application would be from the construction world, where when we're determining a rafter or pitch of a roof, we're looking at the rise and the run. The rise and run are the equivalent of the legs of a right triangle, where the length of the rafter is the hypotenuse. It can be useful to know that the sum of the angles of any triangle is equal to 180 degrees. In this example, we're looking for the measure of the angle at vertex A. Using the property of the sum of the angles in a triangle equaling 180, we'll replace the two angles that we know with their measurements, subtract those from the 180 will give us the missing angle measurement. And you can check, adding these three measurements up should equal the 180 degrees. When we have a right triangle, we have a theorem that is extremely useful. It's known as the Pythagorean Theorem, and given a right triangle with legs length A and B and the hypotenuse of length C, the following relationship always holds true for a right triangle. Take leg length A and square it, add it to leg B squared. The result is equivalent or equal to the hypotenuse length squared. This is known as the Pythagorean Theorem. Taking away those specific measurements in general terms, sometimes the Pythagorean Theorem will be stated as the sum of the legs squared, sum being the result of an addition, is equal to the hypotenuse squared. Builders use this to determine whether a wall is plumb or perpendicular or not. Here we have a wall that's length 3 feet. An adjacent or hopefully perpendicular wall has a length of 4 feet. And if this is in fact, these walls are perpendicular or forming a right angle, the hypotenuse should have a length of 5. This is verified by using the Pythagorean theorem. If we take each of those leg lengths and square them, 3 squared plus 4 squared added together equals the hypotenuse length of 5 squared. 9, the result of 3 squared, 16, the result of 4 squared, when added together is equal to 25. And this is a gauge often used for construction to determine whether something is plumb or perpendicular. 3, 4, 5, right triangle. When we use the Pythagorean theorem, we can use it for 3 purposes. One is to confirm that a triangle is a right triangle. We can compute the length of the hypotenuse, or the longest length in the right triangle, and we can also compute the length of a leg of a right triangle. Let's look at it to see if we truly have a right triangle. We'll use the basic form of the Pythagorean theorem to do that. The sum of the leg squared is equal to the hypotenuse. And here's an example. Is this a right triangle? In other words, do we have a right angle here being formed? To determine that, we'll take each of the legs, square them, which means we're multiplying them by themselves, 1.9 times 1.9, and so on. Do those legs squared, when added together, equal the hypotenuse squared? Simplifying, 1.9 squared is 3.61, 4.9 squared is 24.01. Adding those together does not result in the hypotenuse measurement, 5.4 squared. When the left side of the formula does not equal the right side of the Pythagorean formula, the triangle is not a right triangle. We do not have a right angle. When we're determining the hypotenuse of a right triangle, we have a variation of the Pythagorean theorem where the rearranged formula looks like this. Taking each of the legs squared, added together, and then taking the square root of the result will give us the hypotenuse. And here's how this works. In this right triangle, we have the leg lengths of 45 and 70 inches, and we want to know the length of the hypotenuse. Using that arrangement of the Pythagorean theorem, we will take each of those leg lengths, the sides that make up the right angle, square each of those, 45 times 45, 70 times 70, adding those two results together gives us 6,925. And the last step then is to take the square root of that sum, which will give us the hypotenuse. This is the longest length in a right triangle, and it should be longer than either of those leg lengths. 83.2 inches is the length of the hypotenuse for this right triangle. The third use for a Pythagorean theorem is to determine a leg length. And here we have a rearrangement of the formula again, where we're solving for one leg, given we know another leg and the hypotenuse lengths. And here's an example how this works. In this right triangle, we do know the hypotenuse and one of the legs. We're looking for the second leg length. Rearranging the Pythagorean theorem gives us this formula where we're going to work on the right-hand side, replacing the hypotenuse with the value from this problem. It needs to be squared, 118 times 118, minus the one leg that we know, 60, needs to be squared. The result is 10,324 after subtracting the square leg from the hypotenuse squared. Last step is to take the square root, and the length of this leg is 101.6 feet. This leg should not be greater than the hypotenuse, since the hypotenuse is always the longest length in a right triangle. You can find additional practice on these types of problems on page 50 and 51.